Hey everyone, this is Dr. Walker. This is video 571 called the Hall effect. The Hall effect is what happens when you have a current carrying conductor placed in an external magnetic field. And what happens is that a potential difference is generated. This picture here on the left shows that you have your conductor. Think of it as a piece of metal that is carrying a current to the right. And there's a voltmeter attached to both ends here. And we see that there's a negative potential difference being generated. On the right-hand side, we see that the charge carriers are positive instead of negative. So they do move in the opposite direction as the negative charges. And the potential difference that is measured is positive. So what we want to do is we want to look at, well, how is this potential difference generated? So let's look at this slide, which is basically the same thing, but it's showing a 3D view so that we can see that the conductor here has some thickness T, and it has a width D here. And it could have either positive or negative charge carriers. So let's look at what happens when the charge carriers are positive. So they will be moving in the same direction as the current. So V sub D, the drift velocity, will be pointing to the right, and the magnetic field is into the page. So use right hand rule number 1. Point your fingers to the right, fold into the page. The magnetic force is the thumb, which is pointing upward. So what's happening is that the positive charge carriers here are being pulled upwards, which means that negative charges accumulate at the bottom here. And you remember from one of the first chapters, right, when we have a separation of charges here, we're going to have an electric field pointing from the positive charge to the negative charge. So what this means is that these positive charges, not only are they experiencing a magnetic force pulling them upward, but positive charges experience a force in the same direction as the electric field. So they're also experiencing an electric force pointing downward. And the positive charges keep accumulating at the top here until the two forces balance each other and they're in equilibrium. And we know that once there is a separation of charges, there is going to be a potential difference between the two ends of this conductor. And so that's the Hall effect, is this potential difference, which we call a Hall voltage, being generated. If we consider negative charges as being the charge carriers, it's going to be the same thing happening, except that the negative charges are going to be experiencing a magnetic force upward. You can check it using the right-hand rule. I'll leave you to do that. And so if the negative charges are the charge carriers, we'll have negative charges accumulating on the top and positive charges on the bottom. So the potential difference generated will just have the opposite polarity. So what we want to do now is derive an equation for this Hall voltage that is generated. And the first thing we want to do is realize that it happens when the magnetic force balances out the electric force. So we can set up the magnitude of each equal to each other. The magnitude of the magnetic force is QVB, because the cross product cancels out to 1 since V is perpendicular to B. And then the electric force is Q times E by definition. So the charge cancels out, and we get an expression for V, and this is supposed to be VD, right? This is the drift velocity of that positive charge here that we're looking at. So we get an expression for VD, which is equal to E over B. So that can be helpful. If you know the electric and magnetic fields, you can find the drift velocity of the particle. But if you want an expression for the Hall voltage, then and we can call it delta V sub H for Hall voltage. We can use, to find the magnitude of it, is going to be ED. And the electric field, we can see, is B times D here. So it's going to be VB times B, and then that's your electric field, and then times D. So here we have another one expression for the Hall voltage, depending on if we know these variables, but maybe we don't know some of these variables. So what's useful is to also write down another expression for the drift velocity, which we learned back when we looked at current. And VD is equal to I over NQA, right? The current over the charge carrier density times the charge times the cross-sectional area. So we can rewrite this as I over NQ, and then the area is not going to be this big area, right? It's the area through which the charges are flowing here. This is the area, which is the thickness times the width here. So T times D is the area. So we can go ahead and plug that in for the drift velocity here. And we're going to get the Hall voltage is equal to IBD over NQTD. So the D's cancel out. And there we have our expression for another expression for the Hall voltage. So use whichever one is more useful for you depending on what we're given. IB over NQT. And in case you're wondering what's the use of this, well, you can actually measure the Hall voltage very easily, right, using a voltmeter, and you can measure magnetic field, you can measure the current. So setting up one of these actually allows you to figure out the carrier charge density and the charge, and it gives you, multiplied by the charge, it gives you information about the material. You know that if the material is an insulator, for instance, it's going to have a very low N, right? Because it doesn't have free conduction electrons, right? So it allows you, this effect allows you to get information about your sample. Let's look at one more application, which is called the velocity selector. So this is a contraption that consists of perpendicular electric and magnetic fields. So in this case, if we have two charged plates producing an electric field to the right, and there's an external magnetic field going into the page. And this is used to select charged particles of certain velocity. So if you have a bunch of charges that are going through here, then only the ones that have a certain velocity are going to be able to make it straight through. If they don't have a certain velocity, they're going to be deflected. And one way or the other, right? Because you know that only the charges that have a velocity v, whatever that v is, such that that v in that external field makes it that there's a magnetic force to the left, right? Use your right hand rule number 1. If v is up, fold into the page, the magnetic force is to the left. So only the charges that have a specific v that allows the FB to exactly cancel out the FE, the two forces to exactly balance each other, those are the only charges that will go through undeflected. So you might think, well, what's the point of that? Well, we saw earlier the mass spectrometer. We only saw the top part of the mass spectrometer, but you're going to have a velocity selector here that allows you to have charges that have that specific V so that you can go ahead and differentiate between whatever is going through here, or find the charge to mass ratio of the particles that are going through in your mass spectrometer. So that's a good application of the velocity selector that is only allowing charges with a certain velocity to pass through undeflected. Let's look at one your turn. I know I made it seem like the video was done, but we do have one your turn here. It says, which magnetic field, if it's the correct strength, allows the electrons to pass through the charged electrodes without being deflected. So we have to assume that we have an electron here, and which magnetic field is going to allow them to pass through undeflected. So think about it for a second, pause the video, and let's go ahead and take a look at it. So we know that there's an electric field going downwards. So we know that the negative charges are going to experience a force upward, right? Negative charges experience a force in the opposite direction as the electric field. So we want a magnetic force going downward on these electrons. And we want them to perfectly balance each other. So, which way does the field have to go? You can kind of do trial and error, but for instance, you know that the magnetic field cannot go up or down because it can't be parallel. It can't go to the right, because then it would be parallel to B, and then there wouldn't be any force. If the magnetic field went down, well, use your right hand rule, pretend the charge is positive, put your fingers to the right, fold them down, and that would be a force into the page. For a positive charge, it would be a force out of the page for a negative charge. That's not what we want. We don't want a force into or out of the page. So let's look at a field into the page. If we have a field into the page here, what's going to happen? Always, when using the right hand rule, always pretend that it's a positive charge, and then just flip your answer, right? So we have a positive charge moving to the right. We fold our fingers into the page. That's going to be a magnetic force upward, that's our thumb direction, on a positive charge. But since this is a negative charge, that means the magnetic force will be downward, which is what we want. So that is the answer for this one. Good practice using the right hand rule and understanding how a velocity selector works.